From case 3, we have derived the equation to calculate the shear stress in beams, in bended beams. Well, that is tau equals VQ over IB. Right, this B is just here. Okay. So here we can write a more general form of this equation. That is tau equals VQ over IT. And the T is the thickness at the point of the cross section where you're determining the tau. Right. So in a simple case, in a simple cross section at the rectangle shown here, of course the T equals B. But how about if you have a more complicated cross section like an I-beam as shown here? So if you are determining the shear stress at a random point like this, where of course you have the T as denoted here, the T is the thickness. But if you are determining the shear stress here, right, in the flange, and if you're cutting it from here, then you can calculate the area here. So the T will be this large. So this will be the thickness at this point, right? Then, so this is something like our case 2, right? But you can also calculate the shear stress according to a case in our case 1, right? So in there, you're just cutting it in this way. Right? So the area A will be here, and the thickness T will be here. Okay, so you can have different thickness values at the same point. We will give more details in later sections when we talk about combined cross sections. Okay, so here in section 7.2, we will talk about the shear stress in beams with simple sections. Okay, just like rectangular shaped or circular shaped cross sections. Okay. The first slide summarizes the first moment of area Q. Well, as we derived previously, if you calculate the tau, it is equal to VQ over IT. Right. For a section, the V, the I, the T can all be constant, and the Q is only variable. So the key to solve the shear stress is to find the correct Q. Right? So for an arbitrary shape as shown here, right, you need to use integration to find the Q. Obviously, we will not test this in any exam. But for a simple section as shown here, see a rectangular shape. Right? So if you are calculating the Q for a random point, here the random point I mean here. Okay, you have a random point here or here, or here, or here, so any random point along this line, right? So we're calculating the shear stress at a random point here. So we're just cutting it in this way. So you get an area above this cutting line. Then the local centroid is just the center of this area. Then you can calculate the D, right? This is the D. This is the distance from the global centroid to the local centroid. Then the Q can be calculated as area A by the distance D. Right. For a combined section, as shown here, it could be a little bit more complicated, since in this case, if you are calculating the shear stress at a random point here or here, right? So you cut it, then you get an area above the cutting line. It's a T-shaped area. So what you have to do is to divide this T-shaped area into two sub-areas, area 1, area 2. Then you can determine the local centroid, then based on which you can calculate the D1 and the D2, A1 and A2. Then you sum A1 D1 and A2 D2, so you get the overall Q. Right, the Q equals A1 D1 plus A2 D2 in this case. So you can see that the moment of area Q is determined for a certain point in the section. So its value depends on the position of the point where it is evaluated, the Q or the tau is evaluated. But the moment of inertia I here, it is calculated for the entire section, so it's a constant for all the points in the section. The I doesn't depend on the location where you're evaluating the Q or the tau. Okay, so here's the difference between the two section properties, Q and Q and I. So in a simple section like a rectangle, as we derived in case 3, while the Q or tau equals 0 on the top and bottom surface, and reaches its maximum value in the middle, right, at the position of the centroid or the neutral axis, or where the bending stress equals 0. Right? So this is a distribution we derived in case 3. Okay, this slide just provided detailed calculations so you can verify this derivation. Okay, the first case here is just you're calculating the Q on the top, right, through point A. On the top, you can see that the Q equals 0. Then at a position 30 from the top surface, here, point B, so you can calculate the QB, well, which is 255,000, and if you calculate the symmetric point on the other side, point D, you can see that you will get the same result, but a negative sign, right? But the same value, the same magnitude. And when passing through the centroid, you cut half of the area, so you get a QC equals 500,000. Okay, this is the maximum value. Okay, reaching the bottom, you can see you get a 0 again. Okay, so you can see this is this distribution. You get a 0, 0, 0, 0, and QB, QD, the same result, and the maximum value in the middle. It's a symmetric distribution. Okay, in this slide we just provided some detailed values so that you can verify this symmetry of Q distribution or tau distribution. Okay, you can try to do this by yourself. Especially you need to do this calculation, and this calculation to see how you can get the same results. Okay. Then this slide summarizes the maximum Q values for different shapes. Okay, for the rectangular shape, the maximum Q value equals BH square over 8. Okay, we derived this value in case 3. Okay, you can just go back to case 3 to check how did we derive this. And for this solid circular cross section and the hollow circular cross section, we also derived the Q max, which are 1 over 12 d cubic d, and here's the 1 over 12 by d cube minus lowercase d cube. This is external diameter, this is internal diameter. Okay, we derived this. I do not request you to derive this, but you need to keep this in mind. Remember them for your calculations. Okay, keep this in mind because these equations are not available on your formula sheet. Okay, remember them. And later we will give 2 detailed examples to see how can we calculate the shear stress in beams with simple sections. We will do one example with a rectangular section and another with a solid circular cross section.